Hey AP Chemsters, this is Mrs. Vanderlei bringing you Blankwalle 6.4 Part 2. So we left off talking about heat capacity and specific heat capacity and what do those numbers actually mean. The higher the heat capacity, it means the longer it takes for it to, raise a temperature by 1 degree. The lower that constant number is, the quicker it heats up. So go back and look at Bill Nye again if you have any questions over that, because they did, I thought, a nice job at going through some of those situations. So we're going to put this all together. And what does Q mean again? Q will always mean heat, quantity of heat. M will be mass. Notice lowercase m, not capital M. That'd be molarity. And the C with a little s there is the specific heat capacity. Look at the units of that again. If it's the specific heat capacity, it's joules over gram degree C. Sometimes I might get lazy and leave off the S. I apologize for that. But if you have a mass involved, you'll need the specific heat capacity. And then delta T, of course, hope you know, is a change in temperature. And so this is the equation that you'll be using, okay? Q equals MC delta T, all right? Some people call it Q MCAT, all right? So the little delta looks like an A, all right? So heat looks like MCAT. So what we do with this is that we can solve for any of those, really those 4 variables, okay? Most often you'll probably be asked, how much heat was released to heat up so much stuff by this amount of temperature, okay? Sometimes you could be asked, okay, what's the final temperature after this much heat was added to the system? So, just read the question and see what is being asked for, okay? So let's look at problem number 9. Okay, so it's going to be your lucky day. You're going to find a penny, minted before 1982, by the way, in the snow. So obviously the penny is cold, okay? So how much heat is absorbed by the penny from you as it warms from the temperature of the snow, which is negative 8 degrees Celsius, to your body temperature, that's 37 degrees Celsius. Assume the penny is pure copper and has a mass of 3.10 grams. All right. So what do I have here? I have an initial temperature of a final temperature. I know it's copper. I know it's mass. What are they asking for? They're asking for Q. So I believe our equation we're going to want is Q equals MC delta T, right? There we go. So let's see here. What is delta T? Delta T is final minus initial. If you ever have that delta, we've talked about it for delta E already, it's final minus initial, so delta T works exact same way. So what do I have here? Do I know the mass? Yes, I do. It's 3.10 grams. Periodic table, not in this case. Sorry, guys, no moles. What's C? Uh-oh. I need to go look that up. I would go back a few pages in your notes. I bet you find a chart with C there. So why don't you stop this, find it, come back and see what you get. All right, how'd you do? Sorry, I got distracted. What is your C value? Your C, I hope you got was this. That's what I got. Notice I kept my units with it. And then here is your delta T. What do you notice here? Okay, look at your units again. So notice that grams cancels out. Notice that degrees Celsius is going to cancel out after I subtract. And so what unit is left? Your unit left is joules, and that's what you are looking for. So it works out pretty well, okay? So now what? Do your math. Go ahead and do your math real quick. And this is what I got. I hope you got that too. So what does this mean? Okay, what does this mean? That if Q is positive, go back a few pages. Again, if Q or W or E is positive, it means something is coming into the system. All right, and so in this case, if Q is positive, that means energy is being, or heat is being gained by the penny from the surroundings. Hey, that's you, isn't it? So that means energy is going into the penny. Okay, so let's look at problem number 10. Okay, so basically what's going on here is that you find a rock and you're hoping it's gold. Wouldn't that be pretty cool if it were, okay? So being the chemist that you are, you perform this experiment on it, okay? You weigh it, you put some heat into it, you find out the change in temperature, and you're going to find its heat capacity. And then you're going to compare it with actual gold. So why don't you go ahead and set this problem, solve for the heat capacity, go back and look on the chart, or if you can't find the chart, use your Google, all right, and see if it's the same thing. So pause this, do the work, come back and see how you did. Maybe you're rich. So how'd you do? All right, well, let's find out. Did you use that equation? And maybe use that equation too. But this time, what does it say? She finds that upon what? This is a key word right here, absorption. All right, so what does that mean? That means that Q is positive, all right, because it's been absorbed, okay? So the rock absorbed that much energy. Here's the mass, you're looking for C, and here's your delta T. And when you get it all said and done, that's what I calculated, okay? So when you looked up what a gold was somewhere along the line, you should find out that gold is this. So is your rock gold? And the answer is sadly no. All right, sorry, you're not rich. Let's go on to the next page. All right, so now you have an aluminum block, 55 grams. It starts initially at 27.5, absorbs 725 joules of heat. What is the final temperature? So what are you going to do? Well, probably using MC delta T. And what do I have right now? That's my formula. So what I would like you to do is plug in your numbers. And what are you solving for? You're solving for TF. Use your algebra skills and carefully solve for TF. Think about how you're going to do this algebraically. When you come back, then we're going to talk about how I did it, okay? All right, so again, I set it up this way. I'm absorbing 725 joules. Here's my mass. I looked this up for aluminum. Remember, my formula is TF minus T initial, and they told me this is my initial. So how did I do this? Well, my first step is to multiply 55 times 0.903. And I got, I guess I have two equal signs, 49.66 joules per degree Celsius. What happened to my unit? Well, if you look, what happened is that my grams canceled out, didn't they? So I'm left with joules over grams degrees Celsius. And then what did I do? Well, I'm still solving here. So at this point, what I did, you can do it one of two ways. Do you want to distribute this now? You can, all right, and then, work with this. What I did is I divided both sides by 49.66. So that means this gets wiped out, and I put 725 divided by roughly 50. And so that's where I got this. Notice my joules canceled out when I divided both sides by that, so all I'm left with is degrees Celsius, and that is equal to, oops, somewhere's my equal sign, there it is, that is equal to here. So now what? I'm going to add 27.5 to both sides, and I got this. Now, does that make sense? Should be higher than what you started with, shouldn't it? Okay, because you absorbed energy. So that's how I did it. If you distributed in this step first, I think you can, but it's probably going to be a little bit more difficult in the long run. I don't know, maybe not, but that's, again, one way to do this. So why don't you try out problem number 12? Suppose you are cold weather camping and decide to heat some objects to bring into your sleeping bag for warmth. Sounds good. You place a large water jug and a rock of equal mass near the fire. I'm not sure how you did manage that, but okay. Over time, both the rock and the warm get nice and warm and cuddly, okay? But if you can only bring one to your sleeping bag, which one should you choose to keep you the warmest and why? What do you think you're going to look at? I think you're going to look at the specific heat capacity, and there you go. So there's water, and then the one you could look up on the chart was granite. Granite's a type of rock, isn't it? So, I mean, if you picked a different rock, it's probably going to have a very similar heat capacity. So which one, based on these two heat capacities, would you take and put in your sleeping bag? Well, maybe for the same reason I told you about New York City and Albany and Rochester, which one is going to release the heat back the longest? All right, it'll be your water. It's going to take more time to release all that joules of energy, because it has more energy to give off per gram degree Celsius. Okay, so I'd pick the water. That's why they have water jugs, not rock jugs, okay, to keep your feet warm at night. So there you go. I'm going to quit here because part Roman number 4, I think, deserves its own video. So I'm going to stop here. Once again, don't wait to be great, and I'll see you shortly. Bye-bye.